Newton's method. Rather clever way to find the zeros or x-intercepts of a function. Let's have a look at this one to start with. So we're going to find the first positive x-intercept of y equals 2 cos x minus sin x. Now you don't need to know what that graph looks like in order to be able to do it. Let's determine as accurate an estimate as possible by drawing a rough sketch of the graph though. Now if we're going to draw a rough sketch of this graph, we can split it into two graphs. Remember that we're finding the x-intercept when y is 0. So therefore what I'm going to do is I'm going to take that equal to 0 and then I'm going to move sine to that side. So now it's 2 cos x equals sine of x. And for this to be equal to 0, these must be equal the point of intersection of those two graphs. There's 2 cos x and there is sine of x. So approximately 1, 1. There we are. Notice in radians, hey? We don't work in degrees in calculus. So let's put the 1, 1 there. Now, if you look at an exaggerated picture of this graph, it doesn't really matter what it looks like as long as it's curving as it cuts the x-axis. It doesn't matter how you draw it. It's just so that we can get things relative to one another. Right, there's 1, 1 and there's the point there. Now what I'm going to do is I'm going to draw a tangent at that point and I'm going to find its x-intercept. So there's the tangent at that point. Now you notice the useful thing is the x-intercept is actually closer to the x-intercept of the actual graph. So what we're going to do is we're going to find that x value. Then what Newton did is he went there and he said, okay, let's draw a new tangent now, and we're closer over there. All right, let's go there, let's draw a new tangent. And in the end, we get as close to that x-intercept as we wish. So, in order to do the equation of that, in order to find the x-intercept, we need the equation, we need the gradient of that curve, which is related to the derivative, and we need a point. Well, we have the x value, we'll need to find the y value by substitution. So, gradient equals dy by dx. And I've differentiated y equals 2 cos x minus sin x. Well, derivative of 2 cos x is minus 2 sin x. Derivative of minus sin x is minus cos x. Substitute 1, 1 in there. Remember that we're in radians and your calculator must be in radians. And there's your answer. So we now have the gradient of that line. Now we're going to find the y value at this point. So we take 1, 1 and we sub into the original equation and we get the y value. Now we're going to use the old equation y minus y1 equals mx minus x1. So let's just put that up a bit. There we are. Y minus y1, the y value of that point, equals m, the gradient, into x minus x1, the x value of that point. And if we simplify it, there is the equation of that tangent. Now I'm going to find its x-intercept. How do we find an x-intercept? Y equals 0. I'm going to substitute 0 there. I'm going to solve this. I'm not going to worry about showing you the solving. If you cannot solve this equals 0, that's very sad. So therefore now 1,107 is your answer to that, 1.107. So now there's my new line. There we are, 1.107. Now I'm going to start the whole process again. We're going to repeat the process to achieve as accurate an estimate as is needed. Let's look at it theoretically. Right. Let's have a look. Y equals f of x. Let our approximation be a1. Now remember what we did? We found the equation of the tangent at that point. To find the equation we need the gradient. So we substitute it into the derivative. We need the x value. Well, that's the x value. We need the y value, so we substitute that into the original function. So there we are. Y minus y1, well, y1 sub into the original function equals m gradient, substitute into the derivative, into x minus x1. And x1 is that value of a1. If I now find the x-intercept, I'm now going to put y equal to 0. There we are. Y is equal to 0. And let's solve for x. So step 1, well, that 0 doesn't have to be written. I'm going to divide that into here. So I'm going to have f of a1 over f prime of a1 equals x minus a1. Here we are. Then I'm going to take a1 to the other side, but I'm going to flip the equation around the other way just to make it neater. So this says a1 minus the fraction equals x, so therefore x equals a1 minus the fraction. Keep in mind, f of a1 over f prime of a1. That is the formula for Newton's method. There's the more general formula. Any new approximation, an plus 1, is equal to the last approximation, an minus f of an over f prime of an. And that's a very simple formula to use. Let's try it on an example. Here's the parabola, y equals x squared minus x minus 5. We cannot solve that by factorizing. We'd need quadratic formula, but in fact we've been told to use Newton's method. So you may only use Newton's method. You use quadratic formula, you will get no marks. So we need to get an approximation first. So what I'm going to do is I'm going to say, well, let's substitute values in. If x is 0, that's negative. If x is 1, that's still negative. If x is 2, we're still negative. When x is 3, it becomes positive. Oh, 2, negative, 3, we get a positive. So somewhere between 2 and 3. F of 2 is minus 3, f of 3 is 1. So we know that it's going to cross the axis somewhere between those two values. Now, it's closer to 3 because it's 1 there, only 1, so it's just above the x-axis. There's fairly down. So I know it's going to be closer to the value of 3 than the value of 2. So I'm going to say 2,7. Doesn't matter. You could have tried. You could even have 2,1. It would still work. But let's try to get a fairly accurate approximation. Now, there's our formula. New approximation equals old approximation minus f prime. The approximation over f prime, the approximation. Now in this case we have a1, so we're going to find a2. So there's the derivative, 2x minus the original x squared minus x minus 5, a1 squared minus a1 minus 5. The derivative, 2x minus 1, which means twice a1 minus 1. Now, if we substitute that value of a1 into there, we end up with 2,793. So there's our value of a2. Let's store that on the side. There we are. Now I'm going to apply the same formula, where this is now the an, and I'm going to find a3 as the an plus 1. So there we are. a3 equals a2 minus, there's f of a2, there's f prime of a2. And we don't need to do, I don't need to show you that working. We can go straight to the answer, 2,793. Oops, look at this. We have finished. If you substitute that again and again and again, we'll keep getting back 2,793. So there's the answer. We have finished. If you look at quadratic formula, it'll give you the same answer. Let's have a look at a new one now. First positive solution of sine x equals 1 over x. Now what I'm going to do with this one is I'm going to find the x-intercept of y equals sine x minus 1 over x. If you move 1 over x to this side, you'll get sine x minus 1 over x equals naught. So I'm going to say, well, if we had the curve sine x minus 1 over x, we find the x-intercept equal to naught, it'll give you the solution to that equation. So, there we are, f of x equals sine x minus 1 over x. Remember, calculus you can only do in radians. It only has meaning in radians because you cannot divide 1 by degrees. Now, let's draw y equals sine of x, y equals 1 of x, the 1 over x. And there the two graphs are. Notice it's in radians. Pi by 2, the equivalent of 90 degrees. There, this cuts a bit below. There we are. Well, pi by 2, if you use your calculator, is about 1,6. So therefore, I'm going to say that that's about 1,1. I must like 1,1. So I'm now going to use 1,1 as my approximation. Now, A2, new approximation, equals old approximation minus f of old approximation over f prime of old approximation. Now, let's have a look. When we substitute 1,1 there, that's fine. We substitute 1,1 into f of x, so sine of 1,1 over 1 over 1,1. Now, the derivative below will be cos x plus 1 over x squared. Try it, but cos x plus 1 over x squared. Therefore, I'm going to have cos 1,1 plus 1 over 1,1 squared. There is my calculation. And that turns out as 1,11397. Notice I'm going to 5 decimal places because I have to find a correct to 4. Let's not have it compromised by early approximation. Now I'm going to take that value now, and I'm going to use that to find A3. So now we say A3 equals A2 minus f of A2 over f prime of A2. That value goes into here. And we end up with 1,114,157. So what I've done here, I've said A3 equals A2, so I put 1,11397 there, and there. Now I'm going to find A4. I'm going to say A4 equals A3 minus f of A3 over f prime of A3. And when I do that, I end up with 1,114157, and that rings a bell. Have a look here. We've hit the same answer. Now, however many more times we try to substitute, we're going to get that answer. That is the exact value, correct to 6 decimal places, perhaps slightly altered by approximation. So now we're going to go to 4 decimal places, and we're going to be fine. There we are. So x is equal to 1,1142, and that is the first positive solution of that equation. Try it. Use your calculator and see. You will see that it works.